Hello, everyone. We are Group 10, aka the Crunchwrap Supreme, made up of myself, David Pokras,
I am Jake Fulton.
I am Nico Robillos.
I'm Aaron K.
and our project was to build an automatic vegetable cutting/slicing machine.
The goal of our project was to create an automated chopping mechanism that would minimize the risks associated with a person who has impaired mobility when they use a knife. Our CAD design comprised of three major components, put together in the image on the left and exploded on the right, showing the stepper motor and its enclosure, the rail and crank slider, and the base that everything would be attached to. We planned for the mechanism to have the ability to chop virtually any vegetable that someone would need to cook in the kitchen, while maintaining certain safety precautions such as sensors that would detect when the enclosure is removed.
Since we wanted to have our mechanism travel through 2 points during its motion, we decided to design a crank slider mechanism to satisfy a 2-position rocker. We designed our mechanism on SolidWorks and created 2 toggle positions for the cutting motion. We then obtained the lengths of the links by using the bisector method when setting our fixed ground links. Once we obtained the link lengths, we tested to see if the mechanism was a Type 1 Grashof mechanism, and if it wasn't, we moved the ground pivot points and redid the bisector process until our mechanism satisfied the Grashof condition. In determining the lengths of the coupler and crank links, we took the distance from the grounded pivots at each toggle point and plugged them into the equation in the lower right figure. For our first toggle position, we are looking at a 2D and 3D drawing of the links and mechanism at a fully retracted position. At this instance in time, the vegetable will be pushed a certain distance in front of the cutting plane. At the second toggle position, the mechanism is at its fully extended position, and at this time, the tip of the blade will be safely inside the enclosure and would have cut through the vegetable that was pushed into the cutting plane when the mechanism was at its first toggle position.
Here is our position, velocity, and acceleration analysis. In the top left, you'll see the link lengths determined by the graphical synthesis and the omega-2 we assumed from a guess at what motor speed we would need. Also, from the graphical synthesis are the toggle positions highlighted in red and green in the H and I columns of row 1. For simplicity of viewing, theta 2 in degrees is highlighted in yellow in intervals of 10 degrees with the toggle positions shown, but the radian values in column B were used in all the calculations. As soon as we started the analysis, we discovered something interesting. We couldn't exactly determine whether the mechanism was open or crossed for all values of theta 2. To figure it out, we calculated for theta 3 in both cases and compared the results with the expected values obtained in SolidWorks. To the surprise of all team members, the mechanism was crossed for all values of theta 3. We colored the incorrect theta 3 values purple and the actual values green. The green values were then used to solve for d, omega 3, d dot, alpha 3, and d double dot. After the slight confusion with the open and crossed values of theta 3, the rest was pretty smooth sailing. We used the formulas given to us by our professor for the analysis of a crank slider mechanism. We did, however, waste a little bit of time by being unaware that the trigonometric functions built into Excel accept radian values and not degrees. In the end, we got the values we needed and moved on to the force and stress analysis.
The first step when completing our force analysis was to build free body diagrams for each of our significant positions. The free body diagrams that are presented here are from a position in which the blade will first be making contact with the vegetable. With the FBDs done, we can move on to the force equations. After deriving the force equations from the FBDs, we could develop a matrix that will have a total of 8 unknowns and 8 equations, allowing us to solve for our forces. After we completed these steps for both of our most significant positions, we could see that position 2 was clearly the one with greater forces acting upon it, which can be seen from the bottom right figure. This also allowed us to determine the required torque from the motor that we will be using to operate the mechanism. Since position 2 had much greater forces, we moved forward with that scenario when performing the stress analysis. We had first solved for the moments at each significant point to find the critical point. From there, we built a stress diagram and tensor from the expected loading. We solved for uniaxial and bending stress along with shear stress. These could be plugged into the principal stress equation, and then we can move forward with determining safety factor. The equation that we used was a modified Coulomb-Moore equation for our brittle material. Using case 2, we would calculate a safety factor of 1.104.
The entire fabrication process utilized a grand total of 4 materials: wood, PLA plastic, cardboard, and foam. Honestly, there may be more hot glue holding everything together than the last three. The wood was used for the base, the PLA was used to 3D print the 4-bar mechanism, the enclosure for the stepper motor, and the push bar that is attached to the stepper motor. The only use for the cardboard was used to cover the wood surface and build a cable management/control tower. To complete the stress analysis, we used realistic numbers for PLA whenever possible and approximated using PETG elsewhere. We used the ultimate strength for PLA in our calculations from this table we found on the internet. It also confirmed for us that the densities of PETG and PLA are relatively close, so the mass measurements in SolidWorks would not be affected. Since there was no option to select PLA as a material for our 3D modeled parts, we used PETG plastic in SolidWorks, knowing that it was a good approximation. The best method would have been to weigh the actual parts after printing them, but no group member had scales precise enough. The system never failed during testing, so the values we used must have been accurate approximations of the actual values.
As can be seen on the left, we used 5 different sensors along with the limit switches as shown on the right. They are integrated into the stepper motor design. The sled will move forward up until the first limit switch, which will then tell the knife to stop swinging and the stepper motor to move backwards, and we'll move to the final limit switch, which will stop the system completely and move into the initialized state.
One of the most crucial aspects was to ensure that the sum of all forces in the direction normal to the base, for the slider specifically, were equal to 0. In other words, the slider cannot move up or down at any point during operation. We had a few ideas on how to accomplish this and eventually settled on a single rail that would secure the slider to the carriage. The idea for the slider was to screw it into the 4 holes on the carriage to firmly secure it, but designing, printing, and testing 3D printed parts with a team in a global pandemic is difficult. We ended up with a slider that had too small of a base and was secured to the carriage with hot glue and 1 screw. An interesting challenge was how to connect the pieces of the mechanism to each other. Since a normal pin would simply fall out, end caps were designed and printed using interference fits and hot glue to hold everything together and prevent the mechanism from flexing in the Z direction, or the direction normal to the cutting plane. It also took a few test prints to match the crank to the D-shaped output shaft of the motor, and we noticed that even though the final fit was pretty tight, it did seem to wear with use. The DC motor we used had to be in a very specific position as dictated by the kinematic design. We did so by hot gluing and zip tying the motor to a block of wood that was then screwed and hot glued to the base. We accounted for the diameter of the motor body to put the shaft as close to 50 millimeters above the surface of the base and as possible to make sure that the mechanism actually worked. The motor was sourced from an Amazon seller that advertised it as having high torque, yet running it at 100% duty cycle at 12 volts, it could barely cause the mechanism to cut through a banana. We even made sure to run it at half the maximum speed to make use of the motor's maximum torque, but it was still not enough.
When making our final functional prototype, we had to make a few adjustments along the way for our electronics. There are 3 total adjustments. One of them is removing the triple baseboard, which can be seen in the left picture in green. We changed it so that only the microcontroller is now on the breadboards. Additionally, we removed the LM317 that would be used to convert the voltage from 12 to 5 volts after your microcontroller was fried. And finally, we cut down on the amount of wires that were popping off the board and instead made them snug to the breadboard itself.
We began making the physical prototype by splitting into 2 teams consisting of Jake and David and me and Nico. Jake and David were in charge of soldering the connecting pins to the sensors and electronic wires so that they could be connected to the circuit on the breadboard. Meanwhile, Nico and I worked on creating the wood base for all the components to be placed on. As we created the wood base, we realized that we may not have enough room to fit the mechanism, enclosure, and electronics onto the base, so we expanded the base by an additional 8-inch 2x4 piece, as well as adding on a block of wood below the stepper motor enclosure to ensure it would push the vegetables smoothly without issue. The next step was to create the tower that the DC motor would sit on and to ensure that it is both the appropriate height and that the motor itself would not move when it is running the crank slider mechanism. Once this was done and the rail was cut to the correct length and screwed in, we hot glued the enclosure shut, put the electronics into place, and the blade onto the mechanism and tested both the circuit and the code to ensure everything worked as we wanted it to.
As we started to build the prototype, the initial plan was to 3D print all of the parts of the mechanism, but we then realized that the base was going to take about a day and a half to print. In order to avoid that time delay, we cut 3 8-inch pieces from a long 2x4 piece of wood using a chop saw, and screwed them into each other, giving us an 8 by 8 inch base, which was close enough to the dimensions that we were initially going to print. Since the track cutout was going to be printed with the base, we had to find a way to cut out that section from the wood. We planned to use a small rotary grinder to cut out the track section, but after a few minutes of grinding, we realized how inefficient it was. So we decided to cut the entire section from the base and use a chop saw to build the outer parts of the track section and then mounted them back onto the base using screws. Similarly, the fabricated wood base had a different height as we intended it to be, which made our stepper motor enclosure not line up with the top surface of the base. Since the top face of the base sat higher than the original design, we needed to lift the stepper motor enclosure that same distance. In order to do so, we screwed a support block under the enclosure into the back of the base, which held the enclosure flush with the top surface.
The blade went through a few different designs. It was supposed to be a guillotine-shaped piece of steel, but there was no way of obtaining something like that. Instead, we used a piece of acrylic in testing, but it just wasn't sharp enough. We tried a cut-up Arizona iced tea can, but it ended up being too flimsy. We tried reinforcing the Arizona with the acrylic, but by this point, the blade had become misaligned with the blade slot in the stepper motor enclosure. As a final effort, a guillotine-shaped part was 3D printed and had a razor blade glued to it. It managed to go into the blade slot, but it couldn't cut all the way through a banana, and it was still way too flimsy. A future prototype would need a significant slider rework and a properly machined blade in order to be more effective.
In the future, if we were to build this project again, we should allow more time for our 3D printing option. We had to make last-minute changes to the physical prototype because we considered 3D printing later in our design. And though we wanted to go with it because it was easier, we simply did not have the time to 3D print all the components we needed. Also, we should build a physical prototype earlier to work out any issues like space constraints or difficulties with materials that we encountered earlier on in the building process rather than later in a time-constrained manner.
And go. I'll do one after this, right after with the potentiometer, or the